Hello, my name is Ju-Hyung Kim. I'm a postdoc at Seoul National University in South Korea. And today's topic is shear strength modeling for squat walls with boundary elements, which is specialized for walls, safety-related walls in nuclear power plants. And this work is advised by Professor Park at the same university. So these are contents of the presentation. So what was the problem? So about 12 years ago, there was a big earthquake, Tohoku earthquake occurred in Japan, which caused catastrophic disaster of Fukushima nuclear power plants. So that event triggered safety concerns of operating nuclear power plants all over the world, including Korea. So the engineers started to concern the structures are safe, but how safe it is under beyond design earthquakes. So in design perspective, the current design codes, including ACI, successfully provided safe designs, but now we wonder how safe it is. So, and the current designs are very conservative. So as you can see in the second figure, the walls are 4-layered with number 14 bars. And these are very, very, very strong, and combined with the complicated geometry of the walls in the left figure. So the two problems caused the construction quality error problems. And in South Korea, actually, there we found more than 250 voids in containment buildings, which was a very big problem. And so in seismic performance evaluation perspective, as I said earlier, now we have to focus on how safe the nuclear power plant is under beyond design basis earthquakes. So now the key problem in nuclear society is to quantify the uncertainty of the design equations or strength equations, as well as to minimize the safety margins of current equations or uncertainties. And so far, there are several equations that have been developed, proposed by various researchers. And in the table, you can see the large discrepancies between the equations. So basically, the squat walls in nuclear power plants have boundary elements, and they are transfer lateral loading by strut-type mechanism. So all of equations consider vertical rebars in walls, except for ACI. ACI still considers horizontal bars only. And among the 8 equations, the equation proposed by Gulag and Whittaker is the only equation that considers the strength contribution of boundary elements. So again, at the bottom of the flanged wall, ACI design equation for walls consider the concrete and rebars in web only, and the other equations, except for Gulag and Whittaker, neglect the contribution of boundary elements at the end of walls. And this shows a safety factor, the ratio of test results to the prediction. So you can see a large variation depending on the proposed equations. And for ACI, the safety factor for the squat walls with boundary elements was 0.78, which is too conservative for this kind of walls, with COV of 26%. And the large discrepancies between equations are due to, because they are all derived from empirical factors. So they collected their data set and find some empirical factors to optimize their equations. So yeah, so that's why there are so many discrepancies here. So how can you solve the problem? So Professor Park and I tried to develop a simple mechanics-based strength model while directly considering the influence of boundary elements, barbells, or flanges for squat walls, while minimizing the use of empirical factors, so which is that depend on data sets. So we try to develop simplified mechanics-based model. And the result of this study is we developed the mechanical model, and from the model we derived a closed form design equation for practical use. So for several years, we performed this kind of test for nuclear power plants. And if you're interested, you can find 2 papers in ACI, and we figure out 2 typical failure modes for squat walls with boundary elements, which are web crossing on the left and diagonal tension. And particularly for diagonal tension, due to the relatively large horizontal deformation, in-plane deformation of web, you can see the out-of-plane directional failure of boundary elements, and we wanted to quantify the contribution of that part to the shear strength. Yeah, so this is a proposed numerical mechanics-based model, which is just a force equilibrium from the squat wall. So based on the typical crack pattern of squat walls, we divide the wall into 5 constituents. And so according to the force equilibrium, once we get a stress of bars in web, we can successively calculate the stress demands applied to generated to boundary elements. So and modified compression field theory, which is very useful for this kind of in-plane shear problem. So we applied this modified compression field theory to calculate the shear stress, rebar stress of web, and we successively calculate the force demands applied to both boundary elements. And if you're not familiar with MCFT, this paper is a good summary. So you have 5 force equilibrium for the shear panel, like walls in nuclear power plants, and you have 3 strain compatibility conditions and material models for rebars and concrete, considering tension stiffening and compression softening. You can solve the equation simultaneously. You can get shear stress strain behavior of this kind of panel. So using MCFT, you can get a response of web, and by the force equilibrium condition, we can calculate the generated stress at boundary elements. And for example, for compression boundary element, a compressive force is generated, and the in-plane shear deformation of web exerts out-of-plane directional shear for the boundary element. So in summary, the boundary element is subjected to combined shear compression state, and during the test, you can see the very brittle shear compression combined failure mode here. So yeah, so we simplified the behavior from the force equilibrium condition. And similarly, for tension boundary element, the boundary element is subjected to combined tension shear tension state. Yeah, so this model looks simple, but the right-hand side figure shows a real-scale finite element model for nuclear power plants, and you can see the arrows which indicates the reaction force factors at the wall. So when the loading is applied to the right, there's a tension zone almost vertical to the wall, and you have some very horizontal reactions, which is shear, and you have some shear compression combined reaction forces, which are very similar to the simplified equation. So yeah, that's simple, but it's reasonable, which is reasonable. So the strength provided by these squat walls with boundary elements is just the sum of the strengths of 5 segments, which are shear strengths of web and tension boundary element and compression boundary element. But unfortunately, the 5 segments does not fail simultaneously. We need to some iterative calculations until one of the failure of the segment occur. So here's a proposed solution algorithm. So we assume a certain level of shear deformation of web. We calculate the shear stress and bar stress from MCFT and check the stress state of every segment, 5 segments, and we repeat. And no failures occur in every segment. We increase the shear deformation and repeat again until one of the failure occurs. So at that point, from the stress state of each segment, we can calculate the maximum shear strength. So this model was validated using 123 squat walls, which varying from aspect ratio, the ratio of height to the length of the wall from 0.2 to 0.4, and the prediction result was quite reasonable with mean safety factor of 1.12 with and COV coefficient of variation of 16%. And one of the advantage of this model is we can quantify the relative contribution of shear strengths of web and compression boundary element, tension boundary element. So according to the proposed model, the web shear strength contribution was almost proportional to the relative area of the web, and with the median contribution of 58%, which means the web is the still major contribution of shear strength. And for compression boundary element, the contribution of compression boundary element is almost proportional to the size of the compression boundary element, with average contribution of 29%. But for tension boundary element, you can see a relatively large dispersion compared to the compression boundary element. So from the proposed model, we propose a simplified closed form equation which does not require iterations. So from the previous slide, there's a large dispersion of tension boundary element and relatively low contribution. We ignore the contribution of tension boundary element of VTBE, and conservatively we assume that shear strength is just a sum of web shear strength and compression boundary elements shear strength. And in the file long is just the hand calculation of MCFT with some assumptions. So I'm not going into the details for this procedure. So from the numerical model, not from the test result, but from the proposed numerical model, we simplified the strain values of web and boundary elements. So the dots represent the estimated strain values at peak strengths from numerical model, and the solid lines are just a simplification of this distribution just for simplified equation. And by applying this relationship to the modified compression field theory, you can simply derive the shear strength for web. And the interesting thing is that web shear strength is sum of concrete shear strength and rebar shear strength, which is very similar to ACI approach. So the VC, which indicates the shear strength of concrete in web, is a function of tensile strength of concrete with some factors of reinforcement ratios. And for rebar strength, VS, it's just a multiplication of reinforcement ratio and stress of bars. And for compression boundary element, given that compression boundary element is subjected to combined compression shear state, so it's basically a function of compressive strength, but with some reinforcement ratio terms. So the equations are looks a little bit complicated, but these are just requires the geometry of wall and concrete strength, rebar strength, and reinforcement ratio. Just so it's very similar to the conventional equations, but the difference is that we directly consider the influence of boundary element in strength evaluation. Yeah, so the dots indicate the stress of web and boundary elements estimated from proposed numerical model, and the solid lines are from the simplified equation. So with some assumptions, the closed form simplified equation can easily calculate the shear strengths without iterations for shear strengths. So compared to the proposed analytical model, the proposed simplified equation showed a little increased conservatism and variation, but it's still the predictions are very reasonable given that we do not use any empirical factors just from mechanics-based model. And this is a summary of existing equations, and the last two box plots are proposed equations. So as you can see, the proposed models are better or similar to the existing equations, but we do not use the empirical factors, which means that as the test data accumulated, the previous equations may be updated, but our models is just from mechanics, so it's more rigorously derived. So this is according to the proposed model, we directly consider the influence of boundary elements. So in the left-hand side figure, with the increase of boundary element width, BBE, the shear strength is designed to be increased, and for with the increase of vertical bars in web, the strength is also designed to be increased. So still, ACI equations only considers the horizontal bars for scod walls. So that's the point of this proposed equation. So yeah, conclusion. A mechanical-based model was developed to predict the shear strength of scod walls built with boundary elements. And the model was validated and generated strains and stresses to understand the contribution of individual components to overall shear strength, so walls in nuclear power plants. And boundary elements contribute about greater than 40% of total shear strength. So, but the tension boundary element contribution was relatively small and can be neglected for design purpose. And both horizontal and vertical reinforcement ratios affect shear strengths, and the ACI 318 or 345, ignoring vertical reinforcement, should be revised. And the analytical model and simplified design equations showed comparable results with measured capacities and reduced safety factor ratios. Yeah, thank you. That's the end of my presentation.